Now, the difference between 1 and 2 on the practice test is 1, K is very large, 2, K is not large. In other words, strong acid or whatever, strong base, weak acid, weak base. Le Chatelier's principle is going to have an effect on the weak. If it's strong, then there's no impact. So, for example, magnesium hydroxide, if that were soluble, then adding common ion like magnesium chloride would just add to the total magnesium concentration. So let's say I had magnesium hydroxide in there at some molarity and I dumped in some more magnesium, then we expect the total magnesium ion concentration to go up. And the same thing with hydroxide. If I dump in more hydroxide, it would have no impact. But since magnesium hydroxide has a K that's quite small, then we have to worry about the common ion effect and shifting the equilibrium one way or the other. And so in this case, these are basic common ion type problems. So if I have the solubility in pure water, that's going to have the highest solubility. If I try to dissolve this in a magnesium chloride solution, the solubility is going to be lower because of the magnesium ion. There's already a bunch of magnesium ion present. And therefore, we aren't going to be able to dissolve as much. And the same thing, if I tried to dissolve magnesium hydroxide in a solution of potassium hydroxide, common ion effect there. And so these should be 3 quick calculations you should be able to do. These are going to be the case. That's the common ion effect. And then you have to remember the uncommon ion effect or the non-common ion effect. And what is the uncommon ion effect? There should be this is A, B, C, and D. In D, uncommon ion would be something like if I try to dissolve magnesium hydroxide in sodium nitrate. When you make sodium nitrate, that's not going to shift the equilibrium one way or the other, but in fact it does. It shifts the equilibrium each way. And so you can tell me, we aren't going to do an actual calculation for it, but qualitatively, you should be able to tell me which way it shifts.
They're going to shift it to the right.
Yes, it shifts it to the right.
And it's the uncommon ion effect, just like referring to how you can have an ion it's not the same ion, but it could create more hydroxide.
Not that. That would be, we can have something that could create more hydroxide. So for example, if you tried to dissolve this in sodium sulfate, sulfate's a base. Base is hydrolyzed water to produce hydroxide. That additional hydroxide is going to add to the product total here and then kind of inhibit the dissolution of magnesium hydroxide. That would be an uncommon ion that creates a common ion that impacts the equilibrium. The situation with magnesium hydroxide is there is a Le Chatelier shift with uncommon ion because the uncommon ions cluster around the ions. So if you have magnesium ions, then the nitrates would cluster around the magnesium. What that does is it forms these clusters, which lowers what we call the free magnesium ion concentration. As the free magnesium ion concentration is lowered, it shifts the equilibrium to the right, the KSP equilibrium. And the sodium ions will cluster around the hydroxides, and thus lowering the free hydroxide, which in turn lowers the product concentration, which shifts it to the right. That's the uncommon ion effect I talked about last week.
If you have less than 3 magnesium ions, wouldn't that shift it to the left?
No, if you have less, because the magnesium ions are on the right side of the equilibrium. The equilibrium is like this. This is going to free magnesium ions and free hydroxide. So if we lower the hydroxide ion concentration, what's that going to do? It's going to shift it to the right. That's uncommon. How do we lower the hydroxide? By surrounding it with sodium ions. So the hydroxides are kind of stuck in a cluster, and the higher the concentration of uncommon, the more the impact. But this is a minor effect because these sodium ions can be broken away from it. And so this is why I went back to chapter 14 to look at the clusters, because this is how you visualize the uncommon ion effect occurring. And so if you go back to that figure in chapter 14, the one showing the clusters, this is what we're seeing here. It doesn't have to be a common ion, it could be an uncommon ion.
So does it happen with, like, in addition of really
Any ion, yeah. But it's not a significant impact. Can you visualize the curve? Common ion has a significant impact in solubility. So as I increase the magnesium or increase the hydroxide, the solubility shoots way down, right? And so if I increase the concentration of common ion, the solubility goes way down. However, if I increase the concentration of uncommon ion, the concentration goes up slightly, but not much. It's not a huge impact. And so you have to know the relative impact. So this curve, the take-home message of this curve is that the common ion effect is significant. Uncommon ion effect is minor, but we should know it. And so that's why we say the common multiple choice question would be which would show the highest solubility for magnesium hydroxide, A, B, C, or D. D would be a solution of sodium nitrate. Which one would you say? D, right. And so that would be just a very basic question, multiple choice question, dealing with common ion and uncommon ion effect. And so this should be a rapid calculation. Why don't you go ahead and calculate the solubility? I had to go grab my pen. So try to calculate the solubility. These should be quick calcs, I think. I forgot to do that. And so as I was saying, the common ion effect, we're going to see the solubility decrease with magnesium and the hydroxide. And pretty soon we're going to look at pH, how pH impacts the solubility, but we could already see it because the more hydroxide we have, the lower the solubility, the less hydroxide. The more hydroxide, the higher the pH. The less hydroxide, the lower the pH. And so we can see the common ion effect as a function of pH here. Okay, and then we talked about the uncommon ion, which is a minor thing, but it would increase the solubility, but we aren't going to do any calculations for that. You could ask Visual Mintech to do the calculation for that. All right. Next, we'll take a look at 31C. Oh, did we? Okay. We did 35. I didn't do 15, correct? I forgot to do 15. So we did 35. All right.
11, 12, 26, 34, 35.
Okay, 15 I was supposed to do. So I skipped that, but it's good we came back and did that. The common ion effect. E. 44 is the next one I want to do. 44 is in the section titled Fractional Precipitation. And what we did in fractional precipitation, that's what we did when we tried to separate the +3 hydroxides from the +2 hydroxides. That's called a fractional precipitation. And what we did there was we took advantage of the lower solubility of the +3s. And so what we tried to do is adjust the amount of hydroxide so that we could precipitate out the +3s without precipitating out the +2s. So we had to figure out what that was. And this is common, and we could use this method for separation. And so let's take a look at 44 here. So one of the things that was going to be difficult is if we had both chloride and bromide present in our unknown. If you had chloride and bromide present, then you add silver to it, it's going to precipitate out a white and an off-white precipitate. And so it's hard to tell, the difference. But one way we might try to do this is we might try to separate out the chloride from the bromide, or the bromide from the chloride first. Chlorides, bromides, and iodides are all soluble except for silver chloride, silver bromide, and silver iodide. But, if chloride and bromide were equally insoluble, then there's no way to separate it. And so what we're going to do in number 44, we're going to just see, is it feasible to separate these? Is there a big enough difference in the solubility that one might precipitate without the other? And so the first thing we do is just kind of look, silver chloride versus silver bromide. And see, the things that make these tricky are if they split up differently. That's one thing. And the other thing that might make it tricky is if the concentrations are different. So for example, we have a lot more chloride than bromide. And so that could make things difficult in assessing if this is going to work or not without doing a calculation. And so we have a mixture of chloride and bromide in solution here. And the concentration of chloride is higher at 0.250 versus 0.0022. Now, when we do solubility is going to depend on how much ion you have there. And what we're going to do is, in a fractional precipitation, we don't calculate the solubility. We use the solubility to see which one might precipitate out first, but we don't even really do that. And so both of these will form the silver salts, and they're both insoluble. So we're going to have silver chloride that could potentially form here, and we take a look at the KSP, and then we compare that with silver bromide. Now, one thing that makes this easier is that they both split the same. So just we can see which one's going to be more soluble, which one should be less soluble based on the KSP. In other words, when they split like this and ionize in the same way, then then we can compare the KSPs directly. However, if they don't split the same way, then we have to determine which one has a higher solubility by calculation. And so the KSP for silver chloride is 1.8 times 10 to the minus 10. And the KSP for silver bromide is 5.0 times 10 to the minus 13. So which one is more soluble? Well, the one with the bigger KSP, because they both ionize the same way. So silver chloride is more soluble. That means silver bromide should precipitate first. This should precipitate first. Now, the problem is we have a lot less bromide ion. And so that's why I'm going to put it, because it's going to depend on how much bromide we have. If we have a huge amount of chloride, then that could change things. And so what we're going to do next is we're going to do a different kind of calculation. So we were calculating solubilities. Now the next thing we're going to calculate is concentration of silver at which precipitation occurs. And so in this particular problem, in a fractional precipitation problem, don't calculate solubilities. It's just going to confuse you. Because you think you're going to need them, but you don't need the solubilities. We're going to do nothing with that number. Instead, we need to do this. We have to calculate the concentration of silver at which precipitation occurs. So we predict silver bromide precipitates first. And so at what concentration will we see silver bromide precipitation? Well, basically, that's a QSP has got to be greater than KSP type situation. That's what we want. And when that happens is when QSP is equal to KSP. And so what we're going to do is this. We're going to say that, okay, KSP is going to equal the silver ion concentration times the bromide ion concentration. And if I have this situation where KSP is equal to QSP, then we're just saturated. And so what we're going to do is we're going to say that the silver ion concentration to saturate is going to equal KSP divided by the bromide concentration. And so the KSP is 5.0 times 10 to the negative 13, and we just divide it by the bromide ion concentration. Okay, so I'll go 5 times 10 to the minus 13 divided by the bromide ion concentration, which is 0.0022. And that comes out to 2.27 times 10 to the minus 3, 6, 9, 10 times 10 to the minus 10 molar. All right, so what this means is I need a concentration greater than this for precipitation. So if I hit this concentration, it's saturated, it won't precipitate because then QSP is equal to KSP. So what I need to do is I need to go greater than this. Well, it won't be too hard to go greater than that because that's extremely small molarity. So we're going to repeat the calculation. What is the silver ion concentration required to precipitate out silver chloride? Next. So the KSP is going to equal the silver ion concentration times the chloride ion concentration. And we come up with a similar equation here that the silver ion concentration is equal to the KSP divided by the chloride ion concentration. Chloride ion concentration is 0.250, and KSP is 1.8 times 10 to the minus 10. 1.8 times 10 to the minus 10 divided by 0.25. 7.20 times 10 to the minus 10. And so what we need is we need to increase the silver ion concentration above 7.20 times 10 minus 10 to see precipitation of silver chloride. So this is the fractional precipitation time. Fractional precipitation kind of timeline here. So initially we start off with just chloride and bromide in solution. And we have 0 silver ion. And then what we're going to do is we're going to increase the silver ion concentration slowly. This has to be done very slowly. And then we're, at the first point, we're going to hit 2.27 times 10 to the minus 10 molar. So at 2.27 times 10 to the minus 10 molar, we have saturation. Saturated with respect to silver bromide. It's unsaturated with respect to silver chloride. So there's no danger of silver chloride precipitating because we need much higher silver concentration for that. And so what we're going to do is we're going to increase the silver. Now we have to do this extremely slow such that the silver bromide starts to precipitate, but the silver chloride stays in solution. So we get precipitation of silver bromide. We can't keep increasing it indefinitely. Eventually, we're going to hit a point where we're going to get a molarity of silver ion of 7.20 times 10 to the minus 10. We have to stop here. The reason we have to stop here is because the solution becomes saturated with respect to silver chloride. If we continue here, we're going to precipitate both. Because the more silver I have, the less bromide I'm going to have, because the bromide is going to be precipitating. So the silver ion concentration goes up, the bromide concentration goes down. The bromide concentration goes down because of precipitation. So at the stopping point, how much bromide remains? So that's our next calculation. At the stopping point, how much bromide remains? So the bromide concentration that remains is equal to KSP divided by the silver ion concentration at the stopping point. And so the KSP for silver bromide is 5.0 times 10 to the minus 13. And the silver ion concentration at the stopping point is 7.20 times 10 to the minus 10. And so 5 times 10 to the negative 13 divided by 7.2 times 10 to the negative 10. .94 times 10 to the minus 4. Then we calculate the percent bromide remaining. At the stopping point. So that's equal to the bromide ion concentration that remains, 6.94 times 10 to the minus 4 molar, over the initial, which is 0.022. 0.0022 or 0.022? Let's take a look. No, 0.022. In other words, times 100%. This is going to be equal to the concentration of bromide remaining over the concentration of bromide initial times 100%. So it's 6.94 times 10 to the minus 4 divided by 0.022 times 100. 3.15 remains. The next, we calculate the percent bromide precipitated. So only 3% remains. What happened to the rest? Well, the rest precipitated out. And so this is going to be 100% minus 3.15. 100 is exact. And so this is going to be 96.85%. So we got about 97% of the bromide out before chloride begins to precipitate. Let's go to C here. Can the chloride and bromide be separated effectively by fractional precipitation? Well, it depends on what you mean by effective. We can get out about 97% of the bromide, so we'll have pure silver bromide, but there's going to be remaining 3% mixed in with the chloride, and so we'll still end up with a chloride-bromide mixture at the end of this. However, if we can get 99.9% precipitation, fractional precipitation, 99.9% precipitation is desired. That only leaves about 0.1% residual bromide, so the chloride is going to be slightly contaminated, but not by much. And so if we have 99.9%, then we call it a complete separation. But technically it's not complete, but it's complete enough. And at least the bromide is going to be pure. And so this is close, but not quite there. Any questions on this? Now, when you look, like I said, you should look at other problems to see what the other setups are like. So, when you look at fractional precipitations, what are the other problems like? Well, this is trying to separate out chloride and iodide. That might be more effective. This might be more effective because silver iodide has very low solubility. So this could be greater than 99.9%, but it's very similar, 43. If we look at some of the other fractional precipitations like 42, this is for lead chromate and lead sulfate. And so it's basically the same kind of setup. It splits up 1 to 1. to 1. However, 41 is different. When you look at 41, we're forming lead 2 iodide and silver iodide. And so we want to separate lead from silver. Well, one way is by fractional precipitation. Here, it's hard to tell which one's more soluble because they split up differently. But it turns out lead is more soluble. And so here, the equations are slightly different because lead breaks up into 3 ions, whereas silver iodide breaks up into 2. And so that's pretty much the only difference here. The equations are going to be a little bit different because of that. But you're going to calculate the same things. When we do fractional precipitation, we always calculate the silver ion concentrations required for precipitation. We don't calculate the solubilities. The biggest mistake in fractional precipitation, people calculating the solubilities and not being able to get anywhere with those. They don't get anywhere with those because we don't use the solubilities. It's the biggest mistake. It happens all the time. All right. 44. 45. Take a look at next section. Which is pH and solubility. A, B, C, D, E. Let's take a look at 48. To 0.350 liters of 0.150 molar ammonia is added 0.150 liters of 0.100 magnesium chloride. How many grams of ammonium sulfate should be present to prevent precipitation of magnesium hydroxide? So whatever we have is we have magnesium hydroxide here. So one thing we can always do is just generate the KSP equation. Now, how should we handle this particular problem? One is, okay, if I have ammonia here, what's that going to do? Ammonia is a weak base. Weak bases hydrolyze water to produce hydroxide. So this is a common ion problem. This is a common ion problem like I looked at earlier, except rather than saying pH, we have to figure out what the pH of the solution is. Well, figuring out the pH of the solution is like chapter 16 and chapter 17, because in chapter 16 we didn't have solution dilution. Now we have solution dilution and a Kb for ammonia. And so let's go ahead and figure out how much hydroxide we have to begin with and how much magnesium we have to begin with. And so the first step here is solution dilution. So we'll do step I. So it's 350 and 150 is going to make 500, or half a liter. So we're going to have 0.500 liters, 500 milliliters. And then we have to figure out the new concentration. So let's go ahead and figure out the new concentration of ammonia. new concentration of ammonia is going to be a 150 to 500 dilution of 0.150 molar. So let's figure out that is 150 divided by 500 times 0.15. It's 0.0450. Okay, and then the magnesium concentration, which is going to be a, oops, did I get that wrong? 350, shoot, I got that wrong. It should be 350. $350 divided by 500 times 0.15, 0.105, right? 0.105 molar. And then the magnesium is going to be a 150 to 500 dilution of 0.100. .0300. And so the initial magnesium here I'm going to have is going to be 0.0300. But what is the initial hydroxide? That we can figure out here. The initial hydroxide, we're going to have to do a Kb for ammonia. Figure out how much hydroxide we're going to generate. We're starting at 0.105. 0 and 0. Kb for ammonia is 1.8 times 10 to the minus 5. This is going to equal x squared over 0.105 minus x. We're going to have the simplifying assumption. We'll just go ahead and use that and then solve for x. And so 1.8 times 10 to the minus 5 times 0.105 equals, and I'll take the square root of that, 0.00137. This is going to be about 1%. So divided by 0.105 times 100, 1.3%. Which is okay. It's below 5%, so we'll just go ahead and take it. So if we put in 0.00137 here, we're going to calculate Q. And so if we calculate Q, we'll see if Q is greater than K, we get precipitation. If Q is equal to K, or less than K, then we get no precipitation. So Q is just going to equal 0.03 times 0.00137 squared. .00137 squared times 0.03. 5.63 times 10 to the minus 8. Now we need the KSP value for magnesium hydroxide, which we had up earlier. in the previous problem. I guess I didn't write it down, did I? 1.8 times 10 to the minus 11 was it. And so what we say here is that QSP is much greater than KSP. Therefore, precipitation is expected. So we have too much hydroxide. We have to lower the hydroxide. And so how much hydroxide can I have max? Before precipitation occurs. And so what we're going to do is we're going to do a calculation similar to the previous one. And so initially, I'm not going to change that magnesium. It's going to be 0.0300 molar. But for the hydroxide, I'm going to put question mark molar. We're going to figure out what the max is. So we don't want to exceed that maximum here. Okay, so if I want the hydroxide concentration will equal the KSP divided by the magnesium ion concentration, and then we'll take the square root of that. Did I write the, and that comes from the KSP expression here. The KSP expression is equal to the magnesium concentration times the hydroxide ion concentration squared. So I'm just solving for the hydroxide concentration. Yeah. So we have 1.8 times 10 to the minus 11. Now the magnesium concentration is given 0.0300. We're not going to change that, but what we can change is the hydroxide by buffering it. So 1.8 times 10 to the minus 11 divided by 0.03 equals, and then take the square root of that, 2.44 times 10 to the minus 5 molar. Which gives us a POH of 4.610, which gives us a pH of 9.38. And so this is the max hydroxide. Therefore, this is the max pH. If I go above this pH, I'm going to have too much hydroxide, and I will get a precipitate. And so when we did our qualitative analysis, our pH could not exceed 9.38. If our pH exceeded 9.38, then we would have precipitated out magnesium in addition to the others. And so in this particular problem, we have to make sure the pH stays at or below 9.38. Well, how are we going to do that? We're going to use the buffer system here. So the pH max is going to be 9.38, which is going to equal our pKa, and this is going to be the ammonia buffer, where ammonia is the base, ammonium is the acid. Here. The Ka for ammonium is 5.56 times 10 to the minus 10 plus the log of this ratio, base to acid ratio. 9.25 plus the log of the ratio. And then we're going to calculate the base to acid ratio. So the ammonia to ammonium ratio needs to be 10 to the minus, let's see what that comes out to. Plus 9.125. Wait, did I get that right? Actually, this is positive. Positive. I need to flip this. 1.33. This is ammonia to ammonium ratio. So let's go back here. My ammonia is 0.105 molar. And so I need to figure out what the ammonium concentration is going to be. We have 0.105 divided by 1.333. .0787 molar. And then I have to use some dimensional analysis. So they want us to add ammonium sulfate. And so the grams of ammonium sulfate is equal to, I have 0.500 liters of solution. And then the ammonium concentration has got to be 0.0787 moles of ammonium per liter. That gives me my moles of ammonium. And then I know for every 1 mole of ammonium sulfate, I have 2 moles of ammonium ions. And then the molar mass of ammonium sulfate, I'm just going to look that up. So I don't want to. Calculate right now. 132.14. So how many grams does this come out to? Times 0.5 divided by 2 times 132.14. 2.60 grams. We're only allowed 2 sig figs, so 2.6 grams. We have to make an assumption. We assume that the addition of 2.6 grams of ammonium sulfate does not change the volume. So the volume stays at 0.500 liters. If the volume changed, then we would have multiple unknown type problem, where we'd have to figure out what that is. All right, assuming I did the calculations correctly, this is it. So we're just going to make a buffer to make sure that, and that's what we did in lab, you know, but we were just doing it blind. You know, we got the pH to around 7 and then just made it a little bit more basic. And so we should have been safe, you know. Well, we could have gone all the way up to 9. If we'd gone up all the way up to 9, we would have precipitated out more of the 3+, which would have been a cleaner separation. We have things like litmus paper that could have done it. You know, we have litmus paper. It's not litmus red and blue, but what it is pH paper that's impregnated with many different indicators. And so there's a color coding system where you can see, where you can get it to pH 9. And so that's called, show you it is. But it would be a quick way to do it without having to hassle with the pH meter. And so they just put multiple indicators in there to give you different colors. And so we try to get it maybe around 9. Yeah. Or 8 to be safe. That would have been a better option. And it wouldn't have taken too much additional time. Okay, we're going to jump over to 59. So. And we're going to do another fractional precipitation, but this one we're going to control differently. This one's going to be very tricky because what we're going to do is we're going to control the fractional precipitation by controlling pH, but there's no hydroxides. In the previous examples, we had a hydroxide directly there, and so it's easy to see how the pH is going to impact it, you know. But in this case, we're going to try to see if we can separate iron. These are 2+, so iron 2+ and manganese 2+. It's much easier to separate the 3+ from the 2+ because there's usually a pretty big difference in solubilities. But for this one, let's see if we can separate this here. So another fractional precipitation for iron and manganese. And we're going to put the iron concentration here at here we don't have to do any solution dilution. They're just going to tell us it's going to be 0.10 molar. And the manganese concentration is the same at 0.10 molar. And then they're going to throw in some H2S in here, which is going to be at 0.10 molar. Now, there are going to be a number of things with this particular problem. And the first thing is this. These are going to be KSP-Bs. But rather than calling KSP-B, because there's a footnote B, I'm going to call these KSP daggers, double daggers, like this. And the double dagger is for sulfides. And so if I'm looking at precipitating FES, then I want to generate the KSP equation. Now, the KSP equation is going to be, it's going to form Fe2 plus S2 minus. But there's a problem with S2 minus. What is the problem with S2 minus?
Doesn't exist in water.
Yeah, it doesn't exist in water. S2 minus immediately attacks water to form what? this is the wrong equation here. Sulfide immediately attacks to form HS minus and OH minus. So this is what we call KSPA. KSP double dagger. KSP double dagger is going to be the Fe2 plus concentration times the HS minus concentration times the OH minus concentration. Yeah. So, now, when we try to control things with pH, it could be direct, like pH and POH and hydroxide. But in this case, we're going to look at pH and solubility. Some of the cations and anions are acids and bases in themselves. So if we take FeS solid plus H2O liquid, this is going to produce Fe2 plus HS minus plus OH minus. The first thing is pH is hydronium. And so we look at what hydronium reacts with here. In this previous equilibrium, which we call KSP double dagger, hydronium will attack hydroxide on the product side. And what forms when hydronium attacks hydroxide? Water. When you look at this, this is the reverse of KW. And so we call this 1 over KW. KW is two waters forming hydronium and hydroxide due to that collision. But HS minus is also a potential base. It's amphoteric, and so it can be attacked by hydronium as well. And this is going to form H2S and water. When we look at this, this is actually the reverse of the Ka for H2S. The Ka for H2S is H2S plus water makes hydronium and HS minus. And then what we're going to do is we're going to add these three equations here. And so we're going to FeS plus 2 hydroniums is going to produce Fe2 plus H2S. So the water here is going to cancel there, plus 2 waters. This is what we call KSP double dagger A. A stands for acid. And so acid means react hydronium with whatever we can. And that's going to equal KSP double dagger divided by KW times Ka for H2S. We'll generate the exact same equation for manganese. So manganese sulfide plus 2 hydroniums is going to produce Mn2 plus H2S plus 2 waters. KSPA double dagger for this is going to equal the KSP for manganese divided by KW times Ka for H2S. So same equation there. Now, the KSPA expression is going to equal, for iron, will equal Fe2 plus concentration times the H2S concentration divided by the hydronium ion concentration squared. And this KSPA double dagger expression will equal the manganese concentration times the H2S concentration divided by the hydronium ion concentration squared. So the way we're going to do this fractional precipitation is really weird. What we're going to do is we're going to start at very low pH. And so this is the progress for this. So initially we're going to have iron and manganese and H2S. And what we want is we want to start off at a QSP very low. And the way to make QSP very low is to make sure the hydronium is very low. And so we're going to start off with 0 hydronium, let's say. 0 or very low. And then what we're going to do, actually, no, sorry, I need to go backwards on that. We don't want this very small. If hydronium is very small, it's going to make this very big, right? Does that make sense? So this is wrong. We need to start off with a very large concentration of hydronium. Because a very large concentration of hydronium is going to make QSP smaller. And so we want QSP small. Since the other concentrations are fixed, this is our variable, is the hydronium. And so what we want is we start off at very low pH. And what we're going to do is we're going to increase the pH. As we increase the pH, that's going to decrease the hydronium, which makes the denominator smaller, which makes this term bigger. And so we're going to increase the pH. And so the questions we ask is, at what pH will iron 2 precipitate, and at what pH will manganese 2 precipitate? Which precipitates first? Which precipitates first is, we can just do the calculation, or we could just visually see it. Which one's going to precipitate first is they split up in the same way, so we just look at the KSP double dagger or the KSP B from our book. Well, here's manganese already over here. So if you look at manganese 2 sulfide, it has this superscript B, which I talked about last week. But it's 3 times 10 to the minus 14. 10 to the minus 14. If we look at iron, it's 10 to the minus 19. So manganese has a bigger KSP, which means it's more soluble. As long as they split the same, which they do, we can compare the KSPs directly. If they don't split the same, then we should do the calculation. So which one should precipitate out first is the iron. Iron precipitates first. We could do the calculation though, and you should do the calculation. And so the way we do the calculation is we just determine the pHs at which both precipitate. And so why don't you do that here? Let me give you the numbers for the KSPs here. So for the iron, it's 6 times 10 to the minus 19.
Kw is 1.0 times 10 to the minus 14. Ka for H2S is 1.0 times 10 to the minus 7. Let's take a look at manganese. Three times 10 to the minus 14. What was it, 10 to the minus 14 for manganese? Yeah. So let me calculate the numbers here. Let me lose that. So for iron, I have 6 times 10 to the minus 19. 6 times 10 to the minus 19. Divided by Kw, which is 1 times 10 to the negative 14. Divided by Ka, 1 times 10 to the negative 7. And that comes out to 600. For manganese, I have 10 to the minus 14 and 10 to the minus 7 would be 14 and 7 is 21. Positive 21 would be 6, 7. 3 times 10 to the 7. That would be there's a pretty big difference here, 600 versus 30 million. I think we should be able to separate these. So which one precipitates first? The iron should precipitate first. And so why don't you calculate what pH will the iron precipitate? Go ahead and do that. I'm going to pause the recording here. All right, so when we look at the progress of the fractional precipitation, at very low pHs, both of them are dissolved, and then you increase the pH. Oh, yeah, that's great. Thanks. So at what pH does iron begin to precipitate?
I got 3.389.
That's when the iron starts to precipitate? Is that what other people got? Okay. And then iron 2 plus begins to precipitate. And then what did you do here? What was the stopping pH?
Well, I found the pH for the manganese.
All right.
And I got 4.78 or 4.738.
That's what you got too? Okay. Here we can't go above this. Manganese 2 plus is saturated. So this is the stopping pH, because if we go above this, what's going to happen? if we go above this pH, both manganese and iron precipitate. And so we have to stop here to prevent manganese from precipitating, correct? Yeah, good. And so what was the percent iron remaining at the stopping point?
0.002%.
Oh, shoot. Hopefully, Word can handle this. Point, what was it?
0.002%.
So we have 99.998% precipitation of the iron too. This is an effective precipitation. Only 0.002% remains. And so it's just a small impurity in the manganese. And so this was an effective separation. Good. But the equations were kind of tough because we had all those, things to deal with. Okay. See, well, I guess we'll take a break now. It's a good time for a break. Let's take a break for 15 minutes or so. And see if we can actually, we're going to finish up chapter 18 today. It'll be the best. Yeah, chapter 18 test. When you go back through and analyze this particular problem, there are a number of special things to remember about this particular problem. What are the special things that you should remember about this problem? It has sulfides. Whenever we have sulfides, we have to pay attention to the footnote B. And the equation is always going to involve plus water to make HS minus and OH minus. So you have to remember that. And so that's the double dagger. The other thing is the plus the acid. Plus acid means we add hydronium. If we want to see the direct effect of pH, then we need hydronium in there. And so this is called the KSPA. In fact, we could have done this for magnesium hydroxide as well. I'll do this as an aside here. for magnesium hydroxide, we could see directly what goes on with the pH, although this one gets all screwed up. But if we wanted to do a KSPA, then what we do is we do hydronium. And hydronium is going to react with the hydroxide, so we'll need 2 hydroniums to react with the 2 hydroxides, and this is going to produce waters. And so how many waters would we produce here? A total of 4 waters. And so this would be 1 over kW, and then we double the kW, and so we're going to have to square this. Okay? And then we can combine this. If we combine this, then we see, we'll have magnesium hydroxide solid plus 2 hydroniums. The hydroxides cancel, and this is going to give us Mg2 plus 4 waters. So we call this KSPA. It's a KSP mixed with acid. Does that make sense? A KSPA is what we call combined method. The KSP double dagger is combined method also. The sulfide just doesn't last in water. And so this is the combined method. If I look at the final equilibrium here, is there any hydroxide in my final equilibrium? No. There's no hydroxide in my final equilibrium. But would I expect much hydroxide under acid conditions? Would you expect much hydroxide under acid conditions? No, because the acid's going to neutralize the hydroxide. And so the combined method works if we have this sequence. K is small, and then K is very large. So if you look at the first K, this K is small. But if you look at the second K is very, very, very large. Because we're taking strong acid hydronium and strong base hydroxide, so that's triple V large. Well, triple V large is not a qualitative thing, it's quantitative. I could just do 1 times 1 over kW squared. kW is 10 to the minus 14, square that, you get 10 to the 28. So this comes out to 10 to the 28. You see that? And what that means is the hydronium and hydroxide concentrations, or at least the hydroxide should be very small. We expect hydroxide in this equilibrium here, but we don't see it here. Combined only works this way. If the first step is small and the second step is large, then the combined method works. If we go back here, when we look at the KSP equilibrium for iron, KSP equilibrium for iron should contain iron, HS minus, and OH minus. KB was very large for sulfide. Remember KB? And therefore, we combined the KB expression for sulfide and water, and this is why we end up with this weird equation here. But look at the next 2 equations. K is very large for this, and K is very large for the next one. For reaction 2, it's very, very, very large. For reaction 3, it's very, very large. But we can actually get the numbers here. And when we have this situation where the first one's small and the subsequent ones are large, then we can combine the equations. And so this is called the combined method as well. So what we're doing is we're taking 3 equilibria and combining them to make 1. But there's a sacrifice here. In the combined method, some species disappear. What species disappeared in the combined method? Well, the HS minus disappeared. You see, there's no HS minus in our final equilibrium. The only way that the combined method works is if the HS minus concentration is negligible. If the HS minus concentration is negligible, then we don't care, right? What about the OH minus concentration? There's no OH minus concentration in our final equilibrium. The only way that works is if the OH minus concentration is negligible, which it should be in hydronium, right? And so we're okay with the combined method. If the HS minus concentration and the OH minus concentration were significant, then our final equilibrium here is missing those key ingredients, and the combined method would fail. And so the combined method only works if these intermediate species are negligible. And so that's something else that's special about this. So what we did was we took 3 equilibria and made it 1. And so we didn't have to do simultaneous with 3 equilibria. We just combined them into 1 and then solved it. But the assumption has to work. And so that's another way to solve these ice problems, is by using the combined method. By using the combined method, we can have one additional tool for problem solving. Okay, continuing on here. The next section is complex ion equilibria. And so there are 2 major Ks that are introduced in this chapter. One is KSP, which stands for the solubility product, which deals with precipitation dissolution. The other is called KF. And KF is formation, and it's formation of a complex. And so, for example, copper. Copper likes ammonia. It likes 4 ammonias. And we form the tetramine copper ion. How do we know? We can just look this up. You want to look at formation, we'll just take a look at some formation reactions here. And so in Appendix D, we have the KSPs here. And following the KSPs, we have the KFs. So these are the KFs here. So if I want to know, I don't know what complexes form for copper, but I can look them up really quickly here. And these are the common complexes here. So when I look at copper, I see it likes to form a trichlorido, tetracyanide, ethylene diamine tetraacetate, ethylene diamine, amine, and oxoatom complexes. So these are some common complexes for copper. And these are the KF values here. Because I see copper likes to form an amine complex, but silver also likes to form an amine complex. But what about aluminum? When I look at aluminum, do you see an amine complex? No. Aluminum likes to form a hydroxido complex. And so this is what gave us ways to separate certain things. Like certain things form amine complexes. So we could separate, for example, copper from aluminum just by forming an amine complex of copper and leaving the aluminum alone or as a precipitate. Or we can separate other things, for example, hydroxido. When I look at this, there's no hydroxido complex. So if I form a hydroxido complex of aluminum, I could potentially separate it from the others. And so we use this. This is empirical data. Obviously it would be good to see patterns. Like, for example, why doesn't aluminum form an amine complex? If we understood that, then we can predict, what's your prediction? Will aluminum form an amine complex? How about chromium? Will chromium form an amine complex? What's your prediction? And so we don't have any patterns here. I mean, we could study this data here and then look for patterns. But for right now, we're just going to use this empirically, because when I look at chromium, it looks like it only forms an EDTA and a hydroxido complex, at least the common ones. But I don't see any amine complex here. This is strictly empirical data. We need a better theoretical understanding of what's going on here in order to make predictions. And we aren't going to have that. And so we just use the data as is. We don't have to understand everything. I mean, of course, it would be great to understand everything at a deeper level, but sometimes we just don't have it. And so here are the complexes, and whether it's 4 coordinates, 6 coordinates, 2 coordinate, whatever, we just get it from here. But you will see some patterns. So for example, platinum 2 likes to form 4 coordinate, whereas platinum 4 likes to form 6 coordinate. You know, nickel likes to form 4 coordinate. You see certain patterns there, and 6 coordinate here. So we could try to use some of those, but it's difficult to do, to find a good pattern. And so let's go to complex ion equilibria. And we're going to take a look at 54. Okay, when we look at 54, there's some terms that we have here. Free versus complex. So over here, we call this the free copper. And over here, we call this complex copper. And the total amount of copper we have in solution, we combine it. The free and the complex combined gives us the total. And the same thing with ammonia. We have free ammonia molecules here, and then we have complex ammonia. And the total ammonia we have to add in solution is the combined free and complex. It's going to give us the total. And so they're asking us to calculate the copper 2 free in 0.10 molar copper 2 sulfate solution that is also 6.0 molar in free ammonia. And so we have to understand, is that an equilibrium or is that an initial? And so that's likely at initial. So the initial copper is 0.10 molar. And the initial free is 6.0 molar. And what's going to happen is the ammonia is going to complex the copper 2. And we're going to assume there's 0 molar complex to begin with. If you look at the numbers, KFs are all large. In fact, that's what we should do. We should scan the table and see how big the KFs can get. I mean, 10 to the 13 is a very large number. And so when I look at the KFs, the biggest KF that I see is 10 to the 35 there, 10 to the 42, 10 to the 48. So the biggest one I see is 10 to the 48, and the smallest one is like 10 to the 1. And so KFs in general are big, whereas KSPs in general are small. And so that's a very large number there. If it's a very large number, then I don't want to do it like this. If K is very large, I probably should not start off with everything as reactant because the change is going to be huge. So what do I need to do? Reset. So the first thing we'll do is reset the initial. The limiting reagent here is going to be copper 2 plus. So we're going to go 0 there, and then we need 4 times that. So this is going to be minus 0.4. This is minus 0.1. So if we do a minus, that's going to leave me with 5.6 molar here, and then I'm going to get 0.10 molar here. And so I'd want to reset it. That way the change is going to be small, and hopefully I can use the simplifying assumption. So this is going to be plus x. We're no longer dealing with s right now, and so this is going to be plus 4x, and this is going to be minus x here. So we're going to go to the left. And so we're going to get x molar here, 5.6 plus 4x molar here, and then 0.10 minus x molar here. Now the Kf is going to equal the concentration of the complex divided by the concentration of the copper 2 divided by the concentration of ammonia to the 4th power. So it's going to be 0.10 minus x on the top divided by x, and then 5.6 plus 4x to the fourth. So we're just going to try this simplifying assumption, 0.10 x 5.6 to the fourth, and then solve for x. So I get 1.1 times 10 to the 13. Invert that times 0.1 divided by 5.6 to the fourth. So I get x of that, and then I'll calculate the percent. The bigger percent would be x over 0.1, x over 0.1, or 4x over 5.6. Which one's bigger? I would say that x over 0.1 is going to be bigger. Would you agree? Yeah. So let's go ahead and do that one. We only have to do the bigger one. So divided by 0.1 times 100. 0.133%. So that's okay. Fortunately, the simplifying assumption worked. Otherwise, the math would be pretty difficult. And so we're going to go ahead and plug that in here, 0.000133.5, and then minus 0.1. This is going to come out to 0.099866.5, and then 5.6 plus 4x. So 4 times 0.000133.5 plus 5.6. I get 5.600534. Let's check our K value here. So I'm going to go 5.60034 raised to the fourth power times 0.000133.5. Invert that times 0.099866.5. I'm way off. What did you get for your x? 9.24 times 10 minus 18. Okay.
Shouldn't it be 0.1 divided by 5.6 divided by 1.1?
Yeah, it should be super small. You're right. I think I screwed that up. So it's 0.1 divided by 1.1 times 10 to the positive 13. I probably put negative 13. Habit divided by 5.64. And you got, what did you get? 1.61? 9.24 times 10 minus 18. What did you guys get? Same, Zane? All right. I screwed this up. Well, anyway, the percent change is going to be no problem. That's huge. I mean, that's small, incredibly small. So we're okay. All right, let's go ahead and recalculate these. Sorry. So x is going to be 9.24 times 10 to the minus 18. 5.6, this is going to be about 5.6. And 0.1 minus this is going to be about 0.1, roughly. So let me redo the k calculation. So 0.1 divided by 5.6 to the fourth divided by 9.24 times 10 to the minus 18. 1.1 times 10 to the 3, 6, 9, 12, 13. Yeah, this came out right. 1.10 times 10 to the 13, which is good. So your calculation is accurate. Mine was bad. And so what we can say is, what is the percent remaining? And what is the percent complex? And so let's go ahead and calculate it. Now, the percent remaining, we have to go from the original and compare it to this. And so what is the percent remaining from the original? Is 9.24 times 10 to the minus 18 was the amount I have at the end, and 0.1 was the amount I had at the beginning, times 100%. So this is going to be 10 to the minus 1, 10 squared, 10 cubed, 10 to the minus 15. So this is 9.24 times 10 to the minus 15% remaining. What is the percent complex? Can your calculator do it? The percent complex would be 100 minus 9.24 times 10 to the minus 15. Let me see if my calculator can do it. So 100 minus 9.24 times 10 to the minus 15. Oh, my calculator can't do it. Can yours? No. So the percent complex, well, we could do it by hand. It's going to be 99 point, now I'm going to have 14 zeros, 15 zeros. I need 15 zeros. 1, 2, 3, 4, I mean nines, 15 nines after the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then a 0, 6, whatever. 7, 6, something like that, or about 100%. Something like this. But don't hold it. But your calculator is going to round it off. I mean, your calculator can only carry 10 digits, so it's going to round this. $58. $58. A solution is prepared that has ammonia concentration of 1.00 molar and chloride concentration of 0.100 molar. How many grams of silver nitrate can be dissolved in 1.00 liters of this solution without a precipitate of silver chloride forming? All right, give this one a shot. I forgot to record that. So in this particular problem, we have both a KF and a KSP, so it's difficult. Give it a shot. KSP is small, 10 to the minus 10. KF is big, 10 to the positive 7. We could do combined, then we don't have to worry about simultaneous or stepwise. We couldn't use combined before because we never had that scenario where small and big. You know, we always had small, then smaller, then smallest kind of thing. So number 82 and number 58 are very similar problems. So try 58, and then if you're successful there, then try 82. If you need some hints, let me know. So I just times 143.32, 1.9 milligrams, 0.00192 grams. 1.9 milligrams will dissolve in a liter. But there's a problem with this because this is in water, in pure water. And so in pure water, it's easy to figure out how many grams will dissolve. You know, this is just based on the solubility. The more soluble it is, the more grams will dissolve. So we just need to know the number, the quantitative solubility of this. What's different about this problem? Yeah. In ammonia, what does ammonia do? Yeah. And so what happens is this. This goes back to Le Chatelier's lab. The ammonia is going to remove which species out of the KSP equilibrium? I asked you guys to write the equation. When we wrote the equation earlier, we just say, okay, the silver ion is going to be removed by ammonia, and we're going to form the diamine complex here. Remember doing that? And if we lower the free silver, this equilibrium shifts to the right. Do you remember drawing this equation up? This is from the Le Chatelier's lab. But what we're going to do is we're not going to do this qualitatively. We're going to do this quantitatively. So how do we do this quantitatively? Well, each free silver ion is going to require 2 ammonias, and we're going to form the diamine silver 1 ion. And Kf for this was, what was it? 10 to the 7? 1.6 times 10 to the 7? It's pretty big. Now we have multiple equilibria. With multiple equilibria, we could try to do it stepwise. Stepwise is going to fail. So we have to do this simultaneous. This requires simultaneous. But we're not going to give up yet, because we have one more thing. We should solve these simultaneous. What's that one more trick, not trick, but one more tool that you just learned today that you could try to use? Yeah, the combined method. We call this the SPF equation. It's the SP combined with the F. And that's equal to the KSP times the KF. KSPF will work, but what species is missing from the equilibrium? Silver ion. It will work if we can assume that free silver ion concentration is negligible. There are two ways. One, we don't produce very much. We don't produce very much silver because look at KSP. And two, whatever we produce is quickly attacked by ammonia. Look at KF. And so we could safely assume that the silver ion is negligible, therefore we're going to ignore it from the equilibrium. If we can do that, then we can use the combined method. Can we use the combined method in this case? Yeah, this is a good candidate for the combined method. It should work okay. Here. So all we're going to do is we're going to calculate the solubility now. If we know the solubility, then we can figure out how many grams will dissolve because that's molar solubility. We'll just get gram solubility. So what are our initials? What's the initial ammonia? And we're going to assume nothing's dissolved yet. And then the change is we're going to just let it dissolve. So this is going to be minus 2s plus s plus s. So at equilibrium, I'm going to have 1.00 minus 2s molar ammonia, s molar complex, and s molar chloride. So let me calculate KSPF. KSPF is going to be 1.8 times 10 to the minus 10 times 1.6 times 10 to the positive 7, 0.00288. This is going to equal the complex concentration times the chloride concentration divided by the ammonia concentration squared. Should I reset? Can I reset? No, I can't really reset this. I just got to solve this as is. So this is going to equal s squared over 1 minus 2s squared. Just keep track of sig figs separately. I don't know if the SA will work, but I'm going to try it regardless. So let's go ahead and try the simplifying assumption. Square root of 0.00288. It's not going to work. 0.05. Simplifying assumption failed.
We start off with 0.1 molar.
Oh, do we? I screwed that up, sorry. This is in pure water. In 0.1 molar chloride, this is a common ion effect. It should go down, right? So I need to change this. That's all right. We haven't done the math yet. So this is going to be 0.1 molar chloride, and then this is going to be 0.1 plus S molar chloride. So I already know the simplifying assumption is going to fail, so let me just restart this whole problem. And so KSPF is going to equal S times 0.1 plus S divided by 1 minus 2S quantity squared. Since I have to solve this now, I'm going to go ahead and do this 0.1s plus s squared divided by 1 minus 2s quantity squared. And so I'm just going to multiply it out. This is going to give me 4s squared minus 4s plus 1. Is that right? I think so. But, and that's going to equal 0.00288. All right, so 4 times 0.00288 0.01152 s squared minus 0.1152 s plus 0.00288 there. It's going to equal 0.1 s plus s squared. Okay. So let's subtract this from both sides. This is going to give me 0.09848 s squared. And then add this to both sides, plus 0.11152 s, and then subtract this to both sides, minus 0.00288. 0. We'll go to the quadratic equation solver. Next. Still probably have some more here. $98.48. B 11152. C negative 00288. Calculate. 0.0252, 2526. So the diamine complex should be that, and then this is going to be 0.1 plus that, so 0.12526, and this would be double that. So 2 times 0.02526 minus 1, 94, 94. See what the K comes out to. So I need to square this, invert it, times 0.02526 times 0.15125. 6. $0.003509. which is not the same. Unfortunately, I made a mistake somewhere. Let's see where I made my mistake. So going back to this, 0.1s plus s squared, that looks okay. How about this? Be 4s squared minus 2s minus 2s minus 4s plus 1. Is that correct? And then 4 times 0.00288. Let's see what that comes out to. Oh, 1152, that's right. Oh, 1152 into 00288. Pull 1s plus s squared. And then subtract that from both sides. Oh, I see. I made the mistake here. This is 0.09884. 848. There. 988.48. Sorry. You can come in if you want. 0.025259. 0.025259. That's about the same. Shoot. I'm not going to change it that much. Let's see what it comes out to anyway. Point 0.025259 times 2 from 1 it doesn't really change it at all. Then square this. Invert this times 0.025259 times 0.125259. 3509. Still get the same. What do we have? So I'm still off. Do you guys see my mistake? Well, I know this is off a bit too much. I guess like 351. It should be 288, and so it's off too much. And so all I have to do is I'll have to back up and then see from the beginning here. And so the ammonia was originally 1 molar, the complex at 0, the chloride at 0.1. This is going to be minus, oh, I know what to do. But anyway, we'll get minus 2s plus s plus s. So 1 minus 2s, s 0.1 plus s. That's fine. And then plug that in, s times 0.1 plus s divided by 1 minus 2s squared. And then multiplying out the binomials, what do we get here? Well, we have more tricks that we can use since this is a homework problem. You ever use this? Wolfram alpha? Let's just try this. Enter what you want to calculate. So I want to calculate this. I want to calculate x times, what was it? X times 0.1 plus x. So we'll just do x squared plus 0.1x. So x squared plus 0.1x. That should work. Put in parentheses here. Divided by 1 minus 2x squared is equal to 0.00288. Let's see if we can solve this for us. 0.02166. 0.02166. Oh, 2166. Actually, let me get my quadratic solver and my calculator. Mode 5. Two, 5, 2, 6. I get the same. I screwed up somewhere in this. I don't see it right offhand in these coefficients for this because I'm getting this. Correct answer should be 0.02166. If you pay for the fancy version, it'll go through the algebra for this. We are. But rather than spend too much time looking for my answer, let's double check their answer. So they got 0.02166. So I'm going to try that. 0.02166 times 2. 1, square that, convert that, times 0.02166 times 0.12166. Yeah. So using their numbers, we come up with K value of 0.002879. And that looks good. So I had some algebra problem there. The setup is right, and so this equation is correct, but my answer was incorrect. I'm not seeing it right now, but I'd go back. Anyway, the good thing about double checking is you can go back and check. As long as the setup is okay, you should be okay. But anyway, try number 82, which I wanted to finish off with today. Is that? So you'll need PbCl2, PbCl3 minus. So let's look at the data from Appendix D. So KSP for PbCl2 is 1.6 times 10 to the minus 5. 1.6 times 10 to the minus 5. And the Kf for the trichlorido complex, plumbate 2 complex, is 2.4 times 10 to the first, so 24. So the combined method might have more difficulty with this particular problem because the Kf is not so huge, it's only 24. And the KSP is not so small, it's 10 to the minus 5. The KSPs can get a lot smaller. So this might be pushing the limits of the combined method. But anyway, give it a try using the combined method and see what you get. Maybe I'll try to solve that last problem on paper. Yeah.